All right, let's jump into 4.5 video notes. We're going to learn some more shortcuts today to prove two triangles are congruent. So let me get the full screen going here. All right, so in 4.4, just to kind of highlight, actually I'm going to go back to 4.3. So just to kind of highlight where we've been, 4.3, the only way to prove that two triangles were congruent was to get all 6 parts, and for all 6 parts, meaning I needed to get 3 sides and 3 different angles. Alright, so that's what we had to. Alright, so that was 4.3, and at the bottom of your proof, if you were going to try to find all 6 pieces, your reasoning would be definition of congruent triangles. I don't know why I just do triangle there, but definition of congruent triangles. Now, the only time you're ever going to use that reason in a proof, and the only time you're ever going to want to find 6 parts, was doing the 4.3 practice. But in 4.4, I taught you a couple shortcuts. In 4.4, I said, hey, wait a minute. If you want to prove triangles are congruent, you really don't need 3 or 6 parts. You really only need 3 parts. Now, you had to get the right 3, and we learned side, 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 and side, angle, side. And the key part about that was the angle had to be the included angle. It had to be between or touching both sides. We also learned that ASS does not work. I showed you an example of that, and I also showed you an example of why AAA does not work. So I showed you 2 that worked and 2 that didn't work. Well, it turns out that there's 3 more shortcuts that all work. So the 4.5 notes, just to kind of let the cat out of the bag, as long as you have 2 angles in a side, the order doesn't matter. You can either have 2 angles in the included side or just 2 angles on a random side, and the 2 triangles are definitely going to be congruent. And then there's also this HL theorem, which actually HL, which stands for hypotenuse leg, we'll go into detail in a minute, but HL is actually a special case of a double crooked letter that works. Alright, so HL is a special case of ASS that actually does work. So let's learn about the 3. We're going in a little bit more detail. So theorem 5.10, angle, side, angle, basically says that if you have 2 angles, so notice in this triangle I have 2 angles, congruent with 2 other angles, and I have the side that's included, the side that's touching both of those angles, or the side in between the 2 angles, then the 2 triangles must be congruent. So in a proof, my final step now, I can use ASA if I would like to prove that 2 triangles are congruent. So let's look at the example below and see if we can work one of these out. And remember, you're always looking for a few hidden things as well. You're always looking for some things that I've been referring to as hidden in the diagram. Vertical angles, you always have to keep an eye out for vertical angles. Sometimes that gives you 2 freebies. The reflexive property, which the reflexive property is when you have a shared side. And then also you got to look for parallel lines, because when you have parallel lines, that usually leads you to alternate interior angles. So those are some things to kind of keep your eyes out for. So given the following diagram, is there enough info to show that triangle YZW is congruent to YX or WXY? Justify your answers. Alright, so hint, mark the diagram to show all the known congruencies. Well, I'm looking at this picture, and right now I don't see any congruent markings. I have 0. So I need to come up with some of my own. Well, first of all, the first thing that caught my attention was that I see that WY is congruent to WY, okay, by the reflexive property. Now this isn't really a formal proof, but I'm kind of writing it as if it was a proof just so we get more practice. So that's a side. Now, I look at these parallel lines here. I notice that this line is parallel with this line. And then I have a transversal there that forms a Z. So watch this Z being formed. I have this, the transversal, and this. So the two angles that are involved in that Z are angle 4 and angle 2. And I know that angle 4 must be congruent to angle 2 because they're alternate interior angles. Okay, alternate interior angles. Sometimes I just refer to that as AIA. Just like vertical angles I refer to as VA. I don't mind if you use shortcuts like that. And then by the same token, if I look at this side is parallel with this side, well then we have another Z happening. And I'm going to draw this Z kind of like, so I have parallel line, transversal, parallel line. Well in that Z, I have angle 1 is congruent to angle 3. So angle 1 is congruent to angle 3. And that's also alternate interior angle theorem. So looking now at my triangles and I look at my markings, in the two triangles I do have an angle, the side in between, and an angle. So yes, these two triangles are congruent. Whoa, I started writing a bad word there. Not ASS, but ASA. Angle, side, angle. Alright, moving down to the next example, theorem 5.11. This is the angle, angle, side congruence theorem. Angle, angle, side. So this one says, basically as long as I have any two angles and a non-included side, just some random side somewhere else, that they're also congruent. And when I look at my picture, I have two angles, and instead of having the side in between, I just have a random side up here. So this is an example of AAS. So let's see if we can use that here on this next one. So I see that angle F is congruent to angle K, okay, because all right angles are congruent. That's what you're going to write in your proof. All right angles are congruent. So this is almost, you can treat it like an arc mark. So there's a set that go together. I do see that HG, segment HG, is congruent to itself. That's a reflexive property. Shared side. And finally, I just need to get one more angle. Well, when I focus on the parallel lines, parallel line, transversal, parallel line, I have the Z. So the angles that are equal within that Z would be here and here. Now I can name them by letters. I'm just going to put a number in there. Instead of calling this angle right here FHG, I'm just going to call it angle 1 and say that angle 1 is congruent to angle 2. I think it's cleaner, it's easier. That's alternate interior angles. And now I believe when I look at this triangle on the top up here, this top triangle, I have an angle, and a side that's not included. So this would be two triangles are congruent by angle, angle, side. So if this was a proof, this would actually go over here, and I would say that the triangle is congruent to the triangle on the left hand under my statements. Alright, let's keep on moving down. I believe we have one to go. Hypotenuse leg, the HL. So notice there's only two letters, but actually when you really examine it, there's three parts. It says if hypotenuse and a leg of a right triangle. So that's kind of the third piece. That's why there's not two letters, because you have to know that you have a right angle. So you actually have an angle in there. And as long as you know that one of the legs matches up with the hypotenuse is critical. I have to have a hypotenuse and I have to have a right angle, and then either one of the legs. So let me just draw an example of another one that could work. Basically, if you had the same picture, and as long as you had a right angle, and as long as you have the hypotenuse, you could also have the bottom leg, and either one of these cases would be an example of HL. It can only be used with right triangles. So now if you look at it, it's a special case of ASS. Okay, so HLL is a version of ASS. Okay, but it's a special case of it. So it's a special case that actually works. Most of the time ASS doesn't work, and I showed earlier that if you have a side and then you have an angle right here, that other side, why it didn't work is because you could have one coming this way, or you could decide to swing it out here this way, and you'll have two totally different triangles, okay, because this side here can move. When you force it to be a right angle right there, this side cannot move. It can't swing the way that it did down here. So that's why HL works. So let's look at what we have here. Mark the diagram with the given information, then show the two triangles are congruent. And I'm trying to show, let's first focus on what two triangles, because am I trying to show these two triangles, or am I trying to show something else? Well, let's look at it. We want W, Y, Z. So W to Y to Z. So I want that triangle. These triangles overlap. And whenever I see triangles overlap, a lot of times I redraw this. And I'm going to separate it when I redraw it. So I'm going to redraw W, Z, and Y. So that's Y, that's Z, and that's W. And then I'm going to come back through and I'm going to redraw this triangle, but I'm going to slide it over so that it's out of the way. So let's put it over here so that it's out of the way. And I think when I do proofs, it's always easier to do this. All right. So now let's see what we got. So our given information, first thing is I'm given WY is congruent to XZ. Sweet, I got that. Now my next piece, I'm given that WZ is perpendicular to ZY. WZ to ZY, that's perpendicular. And then I'm also given that XY is perpendicular to ZY. XY perpendicular to ZY. So right now I've used all three pieces of my given. Alright. Now if I wanted to not redraw the picture, my picture would kind of be labeled like this. I'd have a right angle, a right angle. What's hard is marking these hypotenuses. You know, if I do something like this, it's unclear whether it's just this top section of the line right here or whether it's the whole thing. So it's kind of hard to mark it when they're overlapped like that, which is why I normally separate them. Alright, well, we're missing one piece. We have a right angle, check. We have the hypotenuse, check, but I got no leg. So I need to somehow get a leg. How I'm going to get the leg is this common piece right here. This is a shared side. So I can say that ZY is congruent to itself because they share that bottom piece. This is a reflexive property. This is the big move on this one. And once I get that, now I have the two triangles congruent by the HL theorem because I have a hypotenuse and I have that leg. Alright, moving on down. So just to kind of clarify a few things. This is just an example in the notes. I've already talked about this a couple times, but there is no ASS. Now a lot of textbooks write it SSA to be politically correct. I usually write it ASS because you remember that it doesn't work. So here's a triangle that has an angle, a side, and a side, congruent with an angle, a side, and a side. And these two triangles are clearly not the same shape and not the same size. So ASS doesn't work. So down below, and also I might as well just put it in these notes, AAA does not work either. Okay, that one doesn't work because I can have a small triangle, you know, that might be a, say a 30, 60, 90, and then I might have his big brother over here. That's also a 30, 60, 90, and those two triangles are not congruent. They're the same shape, but they're not the same size. So these are the big two that don't work that people try to use, but it's not allowed. So down below, this is basically a summary of what works. side angle side, side side side, hypotenuse leg, right triangles only. As long as you have two angles in the side, it doesn't matter. But you do have to write the proper form in a proof, whether the side is included. So you see how this side is touching both the angles, it's included. Over here, the two angles, the included side we're not counting, that we're doing a non-included side, so that's just AAS. Alright, so pretty short notes today. We're going to keep battling with some more proofs and some mini proofs, so I will see you when you come back to class. Later.